Hello, welcome to another online lecture. Today, we are going to start our computer architecture course, and today's lecture is going to be a brief introduction into the module and what are the various aspects of computer architecture that we'll be looking at in this module. So, this is a second year course that you are following. You may have done a course on computer organization, or at least some aspects of it would have been covered in another course. And in the coming semesters, you may also have another module called operating systems that may build upon this module. So now let's look at what is computer architecture. So as you can see in this diagram, it shows a basic architecture of a building or a house in this case. This is something that you may be aware already, that you may have heard the phrase architecture in this context, that building architects are designing architectures for buildings. And in the context of computers, and when we think about computer architecture, here also we are talking about something similar. We are talking about what are the basic building blocks within that system. In the case of a building, what are the different rooms, what are the different walls, what are the different elements that are there. So that is the architecture. And in the case of a computer, when we talk about computer architecture, it is going to be this. It is going to be this various components that we bring together to build a computer or a device that we call a computer. So, when we think about architecture in the general terms, we say it is the design of the functional structure. So, the design of the structure that we are talking about in a building. And in the case of a computer, we are talking about the various components that bring together a computer system. This includes the logical structures or how the computer is going to do its computational tasks, how it is going to do the calculations and various operations, and also how the various components that are going to be organized. So, this would be how the CPU and various other associated components that are going to be organized. So, when we are talking about computer architecture in this course, we are not talking about various things of computing, such as enclosures or the casings of computers, styling or what is the design, external design of a computer, how it is packaged, various application softwares, power supplies, cooling systems, even peripheral devices. We are not talking about those things in this context. We are mainly looking at the underlying architecture of how a computer functions logically and how it arrives at a decision or computation. So, when we think about a computer, we can think about mainly the hardware. So that is the part that we are talking about in this course. So, we are talking about the hardware that is inside the actual hardware components of the computer. And then we talk about how a software can run on top of that particular hardware. And what are the various hardware design features and how they may impact how a software is running or executing on that particular computer platform. And we are also talking about how various software components may be interacting or interfacing with these hardware components. So in this course, we said we are going to look at computer hardware. So that is our starting point. So from there, we can see the other extreme would be programming or any programming language. You may have been familiar with C, for example, or C++, or some programming language you may have done in a previous course. So the instruction to a computer may start from such a programming language, and we may have to go up to the level of the computer hardware for it to operate on that computing system. So from the programmer's point of view, it is about how the computer system works. They need to know how the computer system works for them to give instructions to that computer to do certain things. From the hardware designer's point of view, they need to know what are the various logical implementations that they have to do inside the circuitry of that computer, inside the processing unit and various other circuitry of the computer. They have to make a decision as to what they are going to do. So whatever that happens in between these two layers, the programming layer and the hardware layer, from the programming layer we have to somehow translate that into something that can be understood by the hardware. So that is somehow translating the programming that we have done in a particular programming language into something that can be understood and executed at the hardware level. And at the hardware level, it has to be designed in such a way so that it can use certain logic gates and various other computing electronic components to accommodate those instructions that are coming from a programming language or a software program written in a programming language. So this middle part, this part that is connecting between these two, is what we would identify as the microarchitect or the architect's view, which is about how the translation between hardware and software can happen. So when we think about computer architecture and computer organization, there are significant differences between these two terminologies. Sometimes it may be possible that you may have used these two terminologies interchangeably, but they are significantly two different things. So, for example, architecture or computer architecture is about the design of the system that is visible to the programmer's view. So, this is about what are the instructions that a particular computer system can execute, how many registers are there in a CPU, how to talk to the memory of a particular computing system. So, these are the things that the architecture of a computer will talk about. On the other hand, if we talk about the organization or computer organization, it is about the details of how a particular computer architecture is implemented. This is about how much cache memory is there, how much or what type of microcode or direct hardware that is available, or what are the various implementation technologies that we have in this system. So, with that computer architecture and computer organization, what we will have is we will have systems where we have the same architecture but different organization. Say, for example, if we think about a PC and if we think about Pentium processors, for example, a lot of Pentium processors follow the same architecture, follow the same Pentium architecture. So even though the various versions of a particular processor may be there, they may still use the same architecture. Say, for example, for a recent example could be the Intel's, again an example from Intel, the core processors, core I processors, so core i3, i5, i7 processors. So these processors all follow the same architecture. So if we write a program to run on one of those computers, it will run on all the computers that follow the same architecture, all the computers that use processors that follow the same architecture. Whereas within those processors, there can be significant differences in terms of the details. So some of those processors may be faster than the others. Some of them may have higher number of cache memories and so on. So these can change. So the main point to remember is architecture would be the underlying design and organization is about how it is implemented. It is about the details of the implementation. So before we go further into the course, one of the questions that you may be having is, why are we studying this course? So, one of the answers may be it is a compulsory module that you have to follow so that you are doing it. But if we think about it, the knowledge that you may get from a computer architecture course would enable you to understand systems better. So it will give you a lot of underlying fundamental details of how computers work, and that will give you the ability to understand various things and various other modules and various other courses that you may be following in the future. This knowledge will be very fundamental and very foundational. And one of the other things could be not all the technologies that you may be using in the future are there today. Say, for example, if we think about 20 years ago, 3D visualizations of virtual reality was not a thing. So, someone who studied at that point in time may not have studied about these things. But if you study the basic foundations of how computers work, it will help you to understand any future technologies where these computing systems may be used. And it will also give you the ability, even if you go into working as a software programmer or software engineer, it will still give you the ability to understand how these systems work, and it will give you the opportunity to perform much better because you have a very good understanding of the underlying architecture on top of which you are developing these software systems. So this is more about the essential course that you need to understand the very basics about computers. So that is the main reason why we are studying this course. So when we think about a basic computing architecture, one of the main architectures or one of the main uh, aspects of computers is about the commonalities that you find in a lot of computers. So, for example, let's think about computers in the case of a laptop that you may be having, a desktop PC if you have one, a mobile computing device like a smartphone that you may have. And if you think about these devices at a very fundamental level, you may see a lot of commonalities among these devices. And the reason for that is a lot of these devices follow what is called a von Neumann architecture. All these devices can be called as von Neumann computers. This is a computer architecture or a design for computers that was developed 50, 60 years ago, and it is still being used in most of the computing devices that we use today. So, the main aspect of von Neumann computers is they have a CPU or a central processing unit or the processor. They will have some form of a memory. It could be temporary memory and also some additional memory that could be long term memory. There would be some form of input devices like a keyboard or a mouse. There could be output devices like displays and printers and so on. And additionally, there could be other networking and communication components. And on top of all of these, there would be software that is connecting all these things and running to achieve certain functionalities in these computers. So that is the basic von Neumann architecture. So that is one of the very foundational architectures of computers that most of the computers that we use follow. And when we think about computers at that type of an abstract level, we can again categorize them into three major categories. So, software, hardware, and instruction set architecture. So, as we previously looked at, there are two sides that we can think of computers. One is how the instructions are generated from software and how those things are executed at a hardware level in the hardware. So, what we have is software. So, these are application software that you may be running, like, say, for example, PowerPoint or Word or a web browser. It could be an operating system that you are running, like Windows or Linux or Mac. It could also be certain firmware that is running on a particular chipset. On the hardware level, it could be various instructions and how they are processed inside the hardware. There could be various input output systems that are enabling communication. There could be various digital logic circuitry, circuit design, and how these things are put together at a hardware level. And the third set of abstraction is what we can call the instruction set architecture. So, this is basically the data types and various instructions that are going to bridge the gap between software and hardware. So, for example, how an application software can talk to a hardware. So, that is what will be given in instruction set architecture. So, one of the things to remember at this point is a lot of these things we will be looking at in more detail in the coming lectures of this course. Today we are going to be briefly look at some of the basic concepts as an introductory point into computer architecture, and more detailed um, modules will be coming in the coming lectures. So this diagram shows a very basic structure of a general computer that you may be very familiar with. So what we have is a CPU or a central processing unit or the processor. We have some cache memory that may be there with the CPU or the processor. We may have input output devices, then they may be connected through some input output controllers. We may have some memory where information can be stored before and after they are executed, and they may be connected through a bus for the communication purposes. All of these things we will look at in much more detail in the coming weeks. All of these components that we have identified in this diagram. But as a starting point, let's briefly look at each of these components, starting with central processing units. So, a CPU is the main computing device that we find in a computer. So this is the one that is going to do the actual computations of a computer. So this is what we call a processor in normal terminologies. And what it has is it will have a control unit that is executing various instructions in a particular order. It will have arithmetic logic units that are actually doing the mathematical and logical computations. It may have some registers or some temporary memory locations where temporary data can be stored, and it can have some additional aspects where um, program counters and various things. We will look at central processing unit in much more detail in the next lecture. Next, we have registers. Registers are temporary data locations or memory locations that are inside CPUs where data is stored before and after it is being processed. Say, for example, if there's an instruction for, say, for example, let's say 2 plus 3. So, before that instruction is executed, it will be stored in registers, and when it is added, and the results can again be stored in a register location. So, it is like a temporary memory location that we can have for that purpose. Then there will be some additional registers that we can identify as special purpose registers. These can be used for actual operation or management of how things are operated in a computer. So these are program counters and various things. Again, we will look at these things in much more detail in the coming week. Next, let's think about what a bus in computer architecture is. It is basically a set of parallel wires that are connecting these various basic components, CPU, memory, and various input output devices, and how these things are connected through some common parallel wires, and those things are called buses or a bus. And a bus is something that, again, we will look at in much more detail in coming weeks. But one of the things to remember is this is where the information is going to flow from one end of the computer. So that is the input output devices to the processing unit, and in between anywhere else like memory locations or storage or wherever it is going to go through these buses. Then we have input output controllers. Input output controllers are devices or controllers that are connecting various input output devices to the main computing system. So, if we think about, again, as any of the other components, this is something that we are going to look at in much more detail in the coming week. But the basic thing that you need to remember is there can be a lot of input output devices in a single computing device, and it may be impractical for all of those things to be individually connected to a computer. So that is where an input output controller comes into play, and it has various other functions as well. But the main thing to remember is these are the ones that are going to manage the communication between the actual input output devices and the main computing system. So the main computing system is going to talk to these input output controllers, and they are in turn going to talk to the actual devices. Say, for example, if you think about a storage device, the storage controller is what the main computing system is going to talk to, and then that storage controller may talk to whatever the storage device, the hard disk or SSD or whatever that is there. The storage controller may be doing the additional talking after that point. So that is the main role of input output controllers. Then we have memory. So memory is something that we all know, that is there can be a number of different types of memory, but the main thing that we are talking about is the random access memory or the internal memory of a computer, where instructions are going to be stored temporarily while they are being executed while the computer is running or the computer system is running. So this is like the main storage point where things are going to be actively used while they are being executed in a computing system. Then, in addition to that main memory or the random access memory, we also can have a lot of additional memory devices attached to a computer. So, in this memory hierarchy that you can see a various number of types of memory devices identified. So, RAM is the main memory that we have identified. So, that is one thing. But other than that, we can also have what is called um, removable memory from the bottom. So, that is any external memory that we are having in these systems. So, that is one thing. Then we can also have storage disk. So, in a computer, it is common to have a hard disk in a computer. Then the RAM is there. Then we can also have a number of cache memory. So, that is again we identified in the basic components. Cache memories are attached to CPU. So, that is there. And then registers, as we looked at some temporary memory locations that can be again used when computations are done. Again, memory hierarchy is something that again we'll look at in much more detail, because that is something that is important to understand for various things when it comes to computing. So that we will look at in much more detail in the coming lectures of this course. So another thing that we identified is, in addition to the hardware and software aspects of a computer, there are what is called instructions. And one of the things that we can sort of briefly look at today is what is called an instruction cycle. So, a basic instruction cycle in a computing device or in a computing system is how a program or set of instructions are going to be executed in that particular computing device. So, the basic instruction cycle is instructions are fetched from a memory address, they are taken from a memory address, then the program counter that identifies which is the instruction is incremented, then that instruction is decoded, relevant operands or instruction inputs are fetched from again memory location, then those instructions are executed and the results are stored back into a memory location. So that is the basic cycle of instruction execution. Again, this is something that we can look at in much more detail in coming weeks. And one of the other things we can remember or we can identify in terms of instructions is what is called a simple model of execution. So, this is about how computing systems keep up with executing various programs or set of instructions within those systems. So, the first thing is the sequence of instructions or how they are going to be executed will have to be controlled so that we know what are the instructions and how, in which order they are being executed. And then we will want to ensure instructions are executed in a particular order. So in a particular given order, one after the other, and only one instruction is executed at a particular time within a particular set of instructions. This is, for example, if you think about any sort of mathematical problem, for example, again, there you may be identifying, say, if there are a number of steps to do a particular computation, you may want to do that in a particular order and one after the other, and that it is better to keep that order going on. So that is the basic simple model of execution in computers as well. So one of the last things that we can sort of identify in terms of the basics of computers or computer systems in the context of computer architecture is how we can identify or categorize various things within these computing systems into various layers or into various levels within how these computers are operating. So, starting from the applications of the software applications, so those are the top level which the user may be interacting with. Then there can be some middle level middleware, again some type of programming things that are there, that are interacting with those application software that a user is using. Then there can be high level languages that through which these programs are created. There can be machine languages that are again low level programming languages which are much closer to what a computing system or the computing hardware may understand. Then there can be microcode, which is the actual code that the hardware may be understanding, or the instructions that can be given to those hardware circuitry, for example. Then there are the actual logic circuitry that is built with AND gates and NAND gates and all these things. Then you have those gates at the next level, and those gates are built using transistors and various other components, and those are again in turn built up with various silicon structures on the basis. So that is a very layered approach of understanding how a computer is structured at various levels, starting from the software level up to the hardware level, up to the silicon level of the hardware. So next, we can look at a brief history of computers. So this is not, as I said, this is an introductory lecture today. So we are mainly going to look at some basic concepts and some basics of computer architecture. This includes some history of computers, and in the coming weeks, we will look at a lot of the concepts and ideas that we looked at previously in much more detail. So today it is going to be brief, and it is going to be briefly about um, these computer architectures and how it has evolved through the history. So when we think about computing in general, we can even start from like the abacus and like all these various old school, not old school, like ancient computing or calculating devices. So these are some type of mechanical devices that may be able to do certain level of computation within themselves. So those are some of those devices. Then this includes like the abacus or the slide rule or adding machines or various things like that. So these are the old school or like ancient devices. Then the actual sort of some form of a computing device we can think of started from what is called the punch card systems that were initially used in looms, also these making clothing materials or those looms. So those are some of the earlier examples of how some level of information is used in some level of operation computation, for example. Then there were some calculating or tabulating devices that were able to do some calculations, computations, and so on. So these are various devices over the time. Some were basic calculators. Again, most of these things used punch cards and various things. And one of the things about punch cards is punch cards even kept on being used in to some extent, uh, recent computing in a sense up to like 70s. Then there was the Charles Babbage computer, which is a mechanical computing device that was in the 1800s. Um, then one of the things again in the context of Charles Babbage's computer is um, there was a woman who did the programming for that particular computer to some extent, who did some form of programming. So that's one of the reasons why she may be considered the first programmer. Then a lot of the modern computings or push towards modern computings came as a result of the Second World War or during the Second World War, when both the fighting parties wanted to find about how they can do encryption, how they can send secret messages, and how they can break those secrets. So that is one of the pushes that led to a lot of inventions and a lot of innovations towards, or things that led to, the modern computing era. And one of the earlier people who were operating in that period was a person called Alan Turing, who developed or invented the Turing machine. And this was the device that was used to break the encryption or the security encryption that were used by the German forces. Around the same time, there were a number of other devices that were being developed by various people in various places. Some of these were academic sort of inventions in universities. Some were developed in academic as academic inventions, but they were mainly targeted as war-related devices, or their intention was to be used in wartime. And after the war, a lot of these devices that were developed during wartime were transferred into, they were like, those devices were there, and they were like, what can we do with these devices? And then there were people identified it is possible for these devices to be used in um, general applications, or in factories, or in organizations, in businesses, in governments. So that's how things progressed into sort of modern computing era. So one of the other things that came about around the same time is the von Neumann architecture that was that we briefly looked at previously. This is one of the main uh, fundamental underlying architectures of computers that we are still using to this day. Then around the same time, there were concepts, or like there were devices that were being developed, that were various sort of memory storage devices that could store um, information permanently. Um, Then, with the invention of transistors, everything changed, because transistors enabled tubes to be removed, because vacuum tubes were the logical computing devices before that point. So, transistors, because they were smaller, cheaper, and they were less heat dissipating, and there were a lot of advantages in using transistors. So, they enabled developing a lot of logic circuitry in much more efficiently, and that led to a lot of development, a lot of fast development into modern computing as we know. Then one of the other things that happened around the same time is um, the development of semiconductor memory. So this is the sort of the memory that we know as of today, but these are the silicon-based or semiconductor-based memory devices that came about around that time. So again, that is something that again pushed the envelope in terms of what can be done, what are the sizes of computers, what are the abilities of computers, and it pushed it gave a lot of advantages into sort of modern computing era. And one of the other things that we can look at is what is called the Moore's law. So Moore's law is something again came about in the early periods of sort of modern computing era, where it was identified that over time the capacity of computers, or like the density of computers, how much computing devices that you can bring into a particular size of a computing device will increase. So we can bring in more and more transistors within a particular size of a chip, and that would enable more and more faster, more and more capable devices being developed. And that is something that we are seeing today as well. Over time, like the computing capabilities keep on improving. So that is what Moore's law identified initially. And one of the other things, again, that was identified from that type of development of computers is um, we would see the development, the CPUs or the processing, computing processing would be much faster. The increase would be much faster than the development in terms of memory. So that is one thing that we are still seeing today. And again, briefly going through sort of the various aspects of computing is the invention of microprocessor is what started, what we can say, what started the personal computing era, where we were able to build smaller computers, at least that can be fit in smaller packages. Then there were the microprocessors that enable these things, from in the 70s from Intel. Then we came about to use parallelism, so where we were able to bring in multiple processors and so on, and how we can bring and operate these things in parallel together. Then we had um, multi-core processors or single-core multi-core processors, where we were able to fit in multiple processors within a single chipset, for example. Then we were able to again bring in multiple processors in parallel and use them. Then we could have additional processors such as GPUs to do graphics processing. And then when we think about the modern processing era, where we have a lot more faster, a lot more denser, a lot more capable processors that can do much more things than the early computers that we may have identified previously. Then the very sort of latest iteration where we are now is the concept of system on a chip, where we are bringing in more and more things of a computer into a single chip and building everything together. And we are seeing a lot of these things in a lot of mobile devices, for example, where the GPU, the memory, the camera module, the networking module, everything is built into a single chipset or single processing unit. So that is again something that we are seeing more and more in the recent times. Then one of the other things that we are seeing recently is the advent of a lot of um, development in terms of large scale memories, faster communication, or faster data transfer within these memory devices or these silicon devices. So that is something again that is happening very recently as well. So what we have identified so far in looking at these history of computing is, I mean, like, the only reason that we looked at the history of computing is for you to get an understanding of how things have progressed over the years. And the main takeaway that I want you all to have from that is there were some technology disruptions that happened over time. So, for example, the transistor was a disruption, microprocessor was a disruption, solid state storage devices were a disruption. So there would be various disruptions that are happening at different points in time in history, and all of these things will change how we interact with computers, how computers interact with us, and how computers are designed and used. And that in turn would influence how the architecture of a computer is coming together as well. So that is one of the things that we will be looking at throughout this course. And one of the concepts that I want you all to identify again, going forward in this course, is about parallelism. And because we mostly will be looking at components on their own, but in many cases these components can be operated, can be designed, and can be communicating in parallel and doing a lot of these things in computers. So that is something that we will be looking at some points uh, in the course as well. But that is something that you need to remember that happens in computers as well. Not all things happen one after the other. A lot of these things can happen in parallel as well. So that brings us to the close of the lecture today. Today, we mainly looked at computer architecture, an introduction into computer architecture, various components that are there as that we can identify as the fundamental architecture of a computer. And in the coming weeks, we will be looking at a lot of these individual components in much more detail. And if you have any questions, ask them through the normal channels or comment here or email me. Other than that, that's all for today. If you have any feedback on this lecture, please let me know. Until I see you next time, this is Nimal. See you.